Good morning. My name is Renelle Miles, and welcome to the Office of Disease Prevention Medicine Mind the Gap seminar series. The Medicine Mind the Gap is a seminar series that explores issues at the intersection of research, evidence, and clinical practice, areas in which conventional wisdom may be contradicted by recent evidence. From the role of advocacy, organizations in medical research and policy to the importance of behavioral interventions, the Office of Disease Prevention hopes to engage the prevention research community in thought-provoking discussions to challenge what we think we know and to think critically about our role in today's research environment. Before we begin, I have some housekeeping items. To participate by Twitter, follow us at NIHPrevents and submit questions using the hashtag NIHMTG. You may also email questions to prevention@mail.nih.gov. There is also a link to a feedback form at the bottom of the videocast page where you can submit questions during the talk. At the conclusion of today's talk, we will open the floor to questions that have been submitted via email and Twitter. Now let me introduce today's speaker. Dr. David Murray has spent his career evaluating intervention programs designed to improve the public health and wrote the first textbook on designing and analyzing group randomized trials. He has worked on many of these trials, collaborating with colleagues around the country on their design, implementation, and evaluation. He has also conducted research to develop and test new methods for their design and analysis. After 35 years at the University of Minnesota, the University of Memphis, and the Ohio State University, Dr. Murray joined the National Institutes of Health in September 2012 as the Associate Director for Prevention and Director of the Office of Disease Prevention. In these roles, he is responsible for promoting and coordinating prevention research among and between NIH institutes and centers and other public and private entities. Consistent with his long-standing involvement in methodological research, one of the strategic priorities for the office is to promote the use of the best available methods in prevention research and to support the development of better methods. At this time, I would like to welcome Dr. Murray and turn the presentation over to him.
Thank you. So I'll speak with you this morning about design and analysis of studies to evaluate multi-level interventions in public health and medicine. Multi-level interventions address more than one level of influence for the targeted outcome. They present a number of special challenges that we don't see in other kinds of studies. The respondents who share the same source of influence at any level will have a number of things in common. It could be physical, could be social, could be other kinds of connections. Those connections create an expectation, at least, for a positive interclass correlation among observations taken from respondents who are members of the same group or get influenced by the same level. That correlation will invalidate many of the usual analytic methods, and so we have to be careful about that. This has to be considered at the planning stage in order to ensure that we have a valid analysis and we have enough power for the analysis that we're going to do. Now, there's a wide variety of design and analytic alternatives that have been suggested, and we're going to start with randomized trials and then move on to other options that have been proposed to evaluate multi-level interventions. This slide shows my own perspective on categorizing randomized trials. I think of three different types. The first are the familiar randomized clinical trials. Here, individuals are randomly assigned to study conditions. There's no interaction among the participants after randomization. This kind of trial is very common with surgical interventions, with drug trials, some behavioral trials. And it is generally considered to be the gold standard for research design in public health and medicine. At the bottom of the slide is the kind of design that I often work with called a group randomized trial. These are also known as cluster randomized trials, sometimes called community trials. There are a variety of labels that are used. The distinguishing characteristic is that groups are randomized to study conditions rather than individuals. It could be work sites, it could be schools, it could be communities, any kind of identifiable social group. And we have the expectation that the members of those groups have been interacting long before we arrive to do the research and will continue to interact during the study and even after we're gone. In between is a hybrid design that has features of both randomized clinical trials and group randomized trials. The individually randomized group treatment trial starts by looking just like an RCT. Individuals are randomized to study conditions. And generally, there's no interaction among the participants at the beginning. However, over the course of the study, participants, at least in the intervention arms, receive some of their intervention, perhaps all of it, in small groups, and interact with one another in those small groups. This is common in weight loss studies and smoking cessation studies, where participants randomized to the intervention arm may choose to come on Tuesday nights for their class on weight loss or weight control or diet and other features. So these kinds of studies start out looking like randomized clinical trials, but take on some of the features of group randomized trials, and they're very common in behavioral studies. Now, what's the impact of the kind of interaction that can happen? Well, with randomized clinical trials and individually randomized trials, there's usually very good opportunity for randomization to work, to distribute all potential sources of bias evenly. If the design is well executed, bias is not usually a concern. That is not the case with group randomized trials, where we usually have a limited number of groups that we're randomizing, and in any single realization of the study, which is the only realization we get to do, there's a limited opportunity for randomization to distribute potential sources of bias. So we have to be more concerned about that in group randomized trials. The impact on the analysis is perhaps more familiar. Observations taken on individuals who don't interact with one another are expected to be independent, and we can use the familiar analytic methods. Anytime, though, that we have members interacting with one another, we have that interclass correlation developing. The observations are no longer independent, and we can't use the usual analytic methods. A little algebra. And all of you have seen at least the first expression, perhaps not in my notation, but in any standard stat textbook. If you're trying to estimate the variance of a group mean, it is the usual variance of the dependent variable divided by the number of observations contributing to the mean. Nothing new there other than notation. When group membership is not established by random assignment, that is, you're working with identifiable groups, pre-existing groups, you have two components of variance, one attributable to groups, one attributable to members. The component attributable to members is divided by the number of observations that define the group mean. The component associated with the group is not. And so the expression is a little bit different. We can write it in an equivalent way, as shown at the bottom of this slide. And this is perhaps the more familiar expression. It's the usual variance of the mean multiplied by this parenthetical expression that includes both an interclass correlation and the number of observations in each of the groups. And here I'm using group to refer to the unit of assignment. I use condition to refer to study arm or treatment arm. So please don't be confused. And when I use the word group, I'm not talking about treatment group and control group. I'm talking about the unit of assignment. The impact on the analysis of this connection and interclass correlation, the variance of any group level statistic will be larger in a group randomized trial than in a randomized clinical trial. Also, the degrees of freedom available to estimate the interclass correlation, or that extra component of variation associated with the groups, is based on the number of groups, and so it's often limited. That's always going to be an issue in a group randomized trial, often an issue in an individually randomized group treatment trial. Any analysis that ignores either the extra variation or the limited degrees of freedom will have an inflated type 1 error rate. This has been established for a long time. I am simply the messenger. Jerome Cornfield talked about this in a paper in 1978 in the American Journal of Epidemiology. Since extra variation and limited degrees of freedom limit power, we have to consider these things at the time the study is designed. Now, many people have looked at those 2 points, the limited degrees of freedom and the extra variation, and said, why should we do these studies? This requires them to be large and expensive and difficult. Well, frankly, they remain the best comparative designs available whenever you have an intervention that you want to evaluate, and that intervention operates at the group level, manipulates the social or physical environment, or simply can't be delivered to individuals without risk of contamination. And that last point is the major driver that pushes investigators to use group randomized trials. Individually randomized group treatment trials, that's the best comparative design if individual randomization is possible without contamination, but if there are good, often logistical reasons to deliver the intervention to small groups. Now, how can we protect the validity of the analysis, since that is the big problem in group randomized trials and individually randomized group treatment trials? Well, one of the most important steps is to avoid misspecifying the analytic model. Every analysis is based on, or most analyses are based on models. Every model is wrong, but many models are useful. And the kind of model that is most useful in this context is a model that accounts for all of the sources of variation in the design. So we need to plan the analysis at the time that we're planning the design, not as an afterthought a year later. We need to plan the analysis around the primary endpoints. If they're dichotomous, that pushes us in one direction. If they're time to event data, it pushes us in a different direction. We need to anticipate all sources of random variation, and this is perhaps the most common mistake that people make, ignoring variability associated with the groups. In every group randomized trial, there are always at least 2 sources of random variation, and in complicated designs, there can be 5 or 7 or more, and we need to account for all of them. It's also important to account for patterns of correlation in the data over time, either among groups or among individuals. It's often helpful to consider alternate models for time, and as in any other field study, it's important to assess potential confounding and effect modification. It's also important in these studies to avoid low power. As the methodologist, my primary concern in these studies is to make sure that the study is designed in a way as to provide adequate power and then analyzed in a way so as to protect the type 1 error rate. I turn to my colleagues who are responsible for creating the intervention and say, please give me an intervention that's going to be effective. I can't perform miracles on the design or analysis side, but my good colleagues on the intervention side, if they provide a strong intervention that has good reach and can be implemented reliably, then we have a chance if I've designed the study correctly. It's very important to have more perhaps smaller groups than to have a few large groups. Power in group randomized trials and individually randomized group treatment trials is driven by the number of groups, not the number of individuals, not the number of members. So one of the studies that I was involved in early on in my career was the Minnesota Heart Health Program. We had 6 communities, measured 20,000 people. We'd never do the study that way again, and NHLBI would never fund it again with that design. Far better to have had 20 communities and far fewer people. But we've learned a lot since 1978 when that application was written. It's important to employ more and smaller surveys or continuous surveillance instead of a few large surveys. And very important, there are analytic tools that we can use to help reduce interclass correlation, reduce variation, and regression adjustment for covariance is one of the most effective strategies and one that I routinely recommend. Let's look at a little bit more algebra. This is the variance of the condition mean in a group randomized trial. And it is the usual variance of the dependent variable, sigma squared y. Divide now, again, by the number of observations contributing to the mean. If I have m members per group and g groups per condition, I have mg observations contributing to a condition mean. That usual variance gets multiplied by this parenthetical expression, 1 plus m minus 1 times the ICC. So it's the number of members in each of the small groups, or each of the units of assignment, and the interclass correlation, and it's really their product. So that parenthetical expression makes the usual variance larger whenever the ICC is positive, which it almost always is, and the impact of a given ICC gets larger as the number of members measured and included in the analysis per group gets larger. So as M and ICC get larger, the variance becomes larger, and that hurts power in the analysis. So this is the simplest expression. It has to be adapted for more complicated analyses, but the basic features are here. We can minimize the variance of the condition mean by minimizing the interclass correlation, by minimizing the variation in the dependent variable, and by maximizing the number of groups in each condition. If we look at how this plays out in example data, we can take a look at the next 3 slides. On the y-axis, we have the detectable difference in standard deviation units, and the scale ranges from 0 to 2.5. If I had an audience, I would ask how many of you have ever had an intervention effect that was 2.5 standard deviation units, and none of you would raise your hand. In public health and medicine, we typically are trying to find evidence to support intervention effects with a detectable difference of about 0.25 standard deviation units, so very much on the lower part of the y-axis. And as you see in this slide, if our interclass correlation happens to be what I consider to be large, 0.1, we're in difficulty, especially if we have a small study. If I only have 2 schools randomized to each arm in my study, I have power to detect an effect of about 1.75 standard deviation units, even with hundreds of people measured in each school. So that's pretty challenging. And I have to have a very large study in order to get a detectable difference that's in the range that I might be able to find. You'll notice that the lines drop as the number of groups per condition goes up. That's the main driver in power for group randomized trials, the number of groups. There is some benefit as we move from left to right in the slide as we increase the number of members per group, but the relative net benefit is much less for increasing members compared to increasing groups. If we work in the more familiar world of a smaller interclass correlation, 0.01 for example, all the lines drop. So the detectable differences that we can find are much smaller. We still can't do very well if we only have 2 groups per condition, but we can do pretty darn well with 8 or 10 or 12, and that is often the number of groups that we need in each of the study conditions in group randomized trials in public health and medicine. The law of diminishing returns is at work here, so if the interclass correlation drops by another order of magnitude, the lines drop, but not by as much, and if I decrease the interclass correlation by another order of magnitude, you'd hardly see a change. So after a point, shrinking that ICC further doesn't help a lot. Now, we've talked a little bit about power, we've talked a little bit in general about analyses. Let's get more concrete and talk about specific kinds of analyses. This is my recommendation for analytic strategies for group randomized trials that have 1 or 2 time intervals that I want to include in the analysis. This could be a post-test only design, it could be a pre-test post-test design where I'm only analyzing the post-test data, or it could be a pre-test post-test design where I'm going to analyze the post-test data and adjust for the baseline measures, or apply a repeated measures approach. Any of those could be used. The key point is that I'm only modeling 1 or 2 time points in the analysis, even if I've collected data at more time points. I can use mixed model analysis of variance and analysis of covariance methods. These are perhaps the most familiar of the methods that are used for group randomized trials. They're fit using the general linear mixed model or the generalized linear mixed model. These are fairly straightforward extensions of the more familiar general linear model and generalized linear model. They accommodate regression adjustment for covariance. That can be very helpful in shrinking interclass correlation. You can't misrepresent the overtime correlation because at most there is 1 in a pre-test post-test design. As I said, it can take several forms. My preferred form is the ANCOVA of post-test data with regression adjustment for pre-test. And if I have 3 or 4 time points, I might pick the last one, or whichever one is most important. That's my outcome, adjust for baseline. So that ANCOVA can be applied even if I have more than 1 time point, or more than 2. Simulations have shown that these methods have the nominal type 1 error rate across a wide range of conditions common in group randomized trials. If I have more than 2 time points that I want to model in the analysis, then I can't use those simple methods. I need to move to what I call random coefficient methods. They're often called growth curve models. Now I'm estimating the intervention effect as a difference in trends that I'm estimating for my 2 conditions. The mixed model ANOVA and ANCOVA methods that work well for the simpler designs don't work well here. They assume that the group-specific trends are the same within each condition, and there's no way to test that. Simulations have shown that if I violate that assumption, I can have an inflated type 1 error rate with the usual mixed model ANOVA, ANCOVA, repeated measures approach to these kinds of designs. So much better to use random coefficients or growth curve models. They avoid those problems. They are used increasingly in the evaluation of public health interventions, and I can recommend them. What about individually randomized group treatment trials? I haven't spoken about them in a few minutes. Many studies randomize participants as individuals, but deliver treatments in small groups. I mentioned psychotherapy trials, weight loss trials, smoking cessation trials. Participants in these studies are nested within those small groups, or they have facilitators that are nested within conditions. There may not be an interclass correlation of any magnitude at baseline, But over time, we can expect that interclass correlation to develop as the interaction within the small groups continues, especially as it is more frequent and more intense and more closely related to the outcome variable. Analyses that ignore that interclass correlation and the degrees of freedom available to estimate it also risk an inflated type 1 error rate. It's not as severe as in a group randomized trial, but it can still be troublesome enough that we need to attend to it. The solution is the same as in group randomized trials. If we're going to use model-based methods, we need to analyze the data to reflect the variation attributable to the small groups. And we need to base degrees of freedom on the number of groups, not just on the number of members. Now, so far I've been talking about group randomized trials, primarily a little bit on individually randomized group treatment trials. Many people have complained to me directly and in the literature that, gosh, David, these studies are big, they're expensive, they're complicated, they require all sorts of difficult methods. Aren't there some simpler alternatives that we can use? And I've listed here a number of alternatives that have been proposed. I'm going to talk about each of these. I talk about them generally in a paper that was published in 2010, and you can see the reference here. Let me mention as well, those that are watching, the references from the presentation will be available with links to PubMed on the ODP website. That may take us a few days to get it up, but we will make it available to you. Let's start by talking about multiple baseline designs. Multiple baseline designs have been suggested as an alternative to group randomized trials. Their main advantage is you don't need many groups. If you're doing a community-wide intervention, you might plan a multiple baseline design that has 3 or 4 communities instead of 8 or 10 or 12 per condition, as is required in a group randomized trial. So the advantage here is you might only need 4 communities instead of needing 20 or 24. Sounds great. Well, you've heard the line about no such thing as free lunch, and unfortunately that applies to many of the alternatives to group randomized trials here, and often will apply to multiple baseline designs. So their main advantage is not many groups. We look at the data to examine changes associated with the introduction of the intervention, and it's easiest to see this in a picture, a figure, so that's what's shown here. This is a hypothetical multiple baseline design with 4 communities. We start collecting data in each of the communities for several months or some period of time until we have a stable baseline pattern in all of the communities. And then we pick one community at random to introduce the intervention. We introduce it. We hope that there is a rapid and appreciable intervention effect that we can see in the data, and you see that in the top panel. We also hope that there is no change in the other communities at the time that we introduce the intervention in community A. We continue to collect data in all of the communities, again, hoping that the pattern is stable, whether it's the intervention effect that we're seeing in community A or the control pattern that we're seeing in the other communities. And then at some point, another community selected at random gets the intervention. We hope to see the same pattern in that community associated with the introduction of the intervention, and no change in the remaining communities. And we keep going. And by the end of the study, we've introduced the intervention in all the communities. If we have this kind of pattern, a very clear change following the introduction of the intervention, no change otherwise, we declare victory, write our paper, and conclude that the intervention had an effect. Now, the evaluation relies on logic, not on statistics. There's no valid statistical analysis here, certainly not with any power, because we don't have many groups. Replication of the pattern in each group, coupled with the absence of that pattern without the intervention, is taken as evidence of the intervention effect, but there aren't statistical results to present. This kind of design is a terrific choice, and I can recommend it if you're confident that your intervention effect is going to be large and rapid and persistent. But I would caution you that it's a poor choice if the effects are expected to be small or gradual, and it's a terrible choice if you think the intervention effect will vary and be inconsistent across the communities that you're working in, because then you won't know what to make of it, and you won't have statistics to help. We published a paper in 2011 detailing the strengths and weaknesses of this approach. Time series designs are often used to evaluate policy change in a single community, often a single state. Examples include evaluation of changes in laws affecting driving age as an attempt to limit morbidity and mortality associated with drink driving, for example. They require, the traditional methods used to evaluate time series designs require repeated and reliable measurements, often 50 or more before the intervention is introduced and again after. So this is not something that you can implement just on the spur of the moment unless you're walking into a situation where those data are available to you in an archive, perhaps data that the state has been collecting anyway. These studies rely on a combination of logic and statistical evidence. I can actually use statistics to show that there was a significant change from pre to post, but without a comparison group, I can't use statistics to judge whether that change is more or less than we would expect absent the intervention. If I have a control series, then I have one group in my treatment arm, one group in my control arm, and there are no valid methods statistically to compare the two arms. So statistical evidence can be limited here, but if you've got the long-term repeated cycles of data and the intervention effect is fairly rapid onset and stable, this approach can be helpful. Quasi-experimental designs are often suggested as alternative to group randomized trials. I like to say that they have all the features of experiments except randomization, and causal inference requires elimination of the plausible alternatives. If groups are assigned and members are observed, and we collect data on the members, the analysis issues and the power issues in a quasi-experiment are the same as in a group randomized trial. So you're not gaining any advantage in terms of power or analytic issues. They're useful if randomization is not possible, but I would argue that well-designed and analyzed quasi-experiments are actually harder to do, often more expensive to do, than well-designed and analyzed group randomized trials. If I need 10 communities in each arm for my group randomized trial, I need the same number in my quasi-experiment for the same level of power. Let me comment on step wedge designs. These are sometimes called dynamic waitlist designs. They're getting increasing attention of late. There was a whole series of papers published recently on step wedge design methods and applications. These studies combine the features of multiple baseline designs and group randomized trials. And certainly, because of the combination, they're more valid than multiple baselines alone, and as good and sometimes better than group randomized trials. Measurement is frequent on the same schedule in all the groups. That's a feature that they have in common with multiple baselines. Time is divided into intervals, again, a feature that they have in common with multiple baselines. Groups are selected at random for the intervention at each interval, either one group or multiple groups. And by the end of the study, all the groups have the intervention. So all of that is in common with multiple baseline designs. This is a picture that explains why it's called stepped wedge. We collect data in all the groups for a while. At some point, one group or multiple groups receive the intervention, and we continue on a staggered schedule until by the end of the study, all of the sites have gotten the intervention. Key features here are that there are many more groups involved than in a multiple baseline design, because this one is powered based on the number of groups, not just a convenient sample of groups or a small sample. I'm introducing the intervention in a random order to the groups. The analysis estimates a weighted average intervention effect across the intervals. It is a combination of a between group effect and a within group effect. This approach will work very well if the intervention effect is fairly rapid and persistent. It's not very sensitive to intervention effects that develop very gradually or fade over time. An important point to acknowledge is that these designs can be more efficient than a group randomized trial, but they usually take longer to complete and may cost more if measurements are expensive. If measurements are not expensive, then costs may not be appreciably different. Again, we have a paper published in 2011 that speaks to some of the details of this kind of design. The last one that I want to talk about is regression discontinuity design. This one is not as well known as it should be in public health and medicine. It's used more in social and behavioral science and in economics. This is a design in which groups or individuals, and you can apply it either at the individual level or the group level, are assigned to conditions based on a quantitative score that often reflects the need for the intervention. Now, you're all sitting there thinking, what? I can give the intervention to the people that need it the most or the groups that need it the most? Yes, that's the way that this design works, and it sounds too good to be true, but it's not. It is actually a true statement. But let's continue. The analysis methods for this design has to follow a couple of very specific rules. There has to be a quantitative score that we're using to assign either the people or the groups to study conditions. We measure all the groups or measure all the people on that quantitative score. We select in advance a cut point in the distribution of the score, and everybody on one side of the score is going to be in the intervention arm, everybody on the other side of the score is going to be in the control arm. And we cannot violate that rule. It has to be rigidly applied. The other requirement in this design is that the analysis has to model the relationship between that assignment score and the outcome quite accurately. If we do both of those things, and follow both of those rules, then the difference in the intercepts at the cutoff is the intervention effect. And this design can provide data that are as valid and as strong as we get in a randomized clinical trial or a group randomized trial. Let's look at an example. The top panel shows what would happen if I measured my assignment variable, shown on the x-axis, and everybody on the left of the midpoint there gets the intervention, everybody on the right gets the control, and the intervention is completely ineffective, has no effect. What you see is that there is a clear relationship between the outcome, the y-axis, and the assignment score, the x-axis. A very good correlation there. If we had put it on the screen, it would probably be 0.9 or better. But it doesn't look like treatment had any effect, because what we see is a relationship between assignment variable and outcome and nothing more. The lower panel shows the way that the data would look if there were a treatment effect. We still see a linear relationship between assignment score and outcome, but now everyone who received the treatment got a boost. That whole line is shifted upwards so that there's a difference in the y-intercepts, and the difference in the y-intercepts is interpreted as the intervention effect. Now, because the assignment to study arms is fully explained by the assignment variable, proper modeling supports causal inference. If you're nervous taking my word for it, maybe you can rely on Don Rubin, who published a paper as long ago as 1977 documenting the validity of this approach. Regression discontinuity designs avoid randomization, but they are as valid as randomized trials if they're properly implemented. There's always a price. The sample size requirements are usually doubled, whether we're talking about the number of people or the number of groups. And we published a paper documenting this approach in group randomized trials in Statistics in Medicine in 2011. A few closing thoughts and then we'll turn to questions. Group randomized trials, individually randomized group treatment trials, stepped wedge designs, regression discontinuity designs, all of these approaches can provide very strong evidence for causal inference if they're implemented and analyzed correctly. It's important to consider the extra variation that we're going to have in the data, the limited degrees of freedom at the design stage. That applies to all of these four options. I recommend that we randomize with stratification on the baseline value of the primary outcome and group size if we can do that. If we don't have the primary outcome at the group level at baseline, let's pick something that we expect to be highly correlated with it. If randomization is not possible, then the regression discontinuity design is the strongest approach, but it requires a larger sample size. I always encourage investigators to blind their evaluation staff to the extent possible. I recognize these are field trials. We can't blind everyone involved. And even if you blind the evaluation staff, they might walk into the schools and the teachers start talking about the wonderful intervention that they did during the year. So blinding can be difficult to maintain. It's important to analyze these studies to account for the extra variation, the limited degrees of freedom, and member level imbalance. I haven't spoken to that in any detail, but that is an important consideration. Other approaches can also provide evidence for causal inference, quasi-experiments, multiple baseline designs, time series designs. but they often rely on logic as much as statistics, and they face more threats to causal inference. So those have to be considered. I have on this slide and the next one a few references, and we're going to post these on the ODP website so that they'll be available to you. Some of these are a little older and some of them are quite new. In fact, the Johnson reference is available online, but it's not appeared in print yet, and a few more here on the next slide. I'd be happy to entertain questions if we have questions that have come in. So let's see what we have.
Okay, our first question is, you said randomization is less effective in group randomized trials compared to traditional RCTs. I'm assuming this is because there are typically few groups, so it's hard for randomization to adequately reduce differences between conditions at baseline. Is there any way to address this?
Your interpretation is absolutely on point. If we have hundreds of groups that we're randomizing, we don't have to worry about confounding. We have the same protection from randomization as we have in a randomized clinical trial that involves hundreds of patients. But with most group randomized trials, the median number of total groups is about 20. So that's 10 per condition. So they're not large, and believe me, if you're only randomly assigning 10 schools to each of 2 arms, a simple random assignment is not going to balance all potential confounders. You will find some important differences on things that you care about if you look at the baseline data. The solution is to use stratified randomization. So stratify your groups in advance, if possible on the primary outcome, if not on something that's related to it. Come up with strata of 4 is my preferred approach. So that means I need multiples of 4 in the design, whether it's 12 or 16 or 20. And then within each stratum of 4, randomly assign 2 and 2 to intervention and control. That will increase the likelihood that at baseline, the 2 conditions will be balanced on whatever it was you stratified on. And if you've stratified on the primary outcome or something highly correlated with it, that will address that issue.
Is it important to take balance into account in the analysis of data from a group randomized trial?
It is. And we have to think about balance at 2 different levels. So let's consider first balance at a group level. So this is the number of schools or work sites or churches that are randomly assigned to each of the study arms. It's very important that that number be the same in each of the conditions. That avoids certain analytical problems that Mitch Gale talked about in a 1996 Statistics in Medicine paper. Did a lovely job in that article. So balance at the group level is very important. I strongly encourage it, and it's usually easy to achieve because the investigator has control over how many get assigned to each arm. So you can usually have balance at that level. Now it's important as you're recruiting and signing up your schools or churches or work sites to, we always had written contracts, a memorandum of understanding, not clearly enforceable, but other than in a moral sense. So the school principal would sign off and say, yes, we agree to do this, and we sign off and say, this is what we're going to do. And that helps keep everybody in the study over the duration. If you have balance on the first day, but you didn't do a very good job of recruiting in a solid way, the groups that you randomize, some of them may drop out, and that can wreck the balance. So important to consider that. Balance at the participant level in a group randomized trial, while most of the papers that you read, the methodological papers that you read, assume that the studies are balanced, that never happens in practice. Schools aren't the same size. The number of kids in the school varies depending on the day that you go in. So there is always variability in the number of members in each of the groups, and that usually translates into variability in the number of members in each condition. If the variability is no worse than about 2 to 1 in terms of the number of members in the largest school compared to the smallest school, or the largest work site and the smallest work site, usually don't have to worry about it. But if the variability is worse than that, and often it is, then you do need to worry about it. I have a paper coming out with Keith Muller, Jackie Johnson, and others in Statistics in Medicine, 2015. It's I think the 3rd reference that's in the reference list for this set of slides, if I can get back to it. Here, Johnson et al., it's the third one in the list. We took a hard look at what happens when there is imbalance, significant imbalance at the member level. Does it matter depending on the magnitude of the interclass correlation? Does it matter depending on a variety of other factors? And we evaluated 10 models that either have been used or could be used to analyze data from a group randomized trial. We determined that none of the methods work very well with very small studies, fewer than 6 groups per condition. If you have serious imbalance, you're in trouble and likely are going to have an inflated type 1 error rate, and there's not a good solution. With 6 or more, we found that an approach that is done in 2 stages that uses weights based on the theoretical variance that allows variance, that constrains variance components to be positive, works very effectively across a range of conditions that we have. A 1-stage model with unconstrained variance components can work well if we have a larger study, 12 or 14 or so groups per arm. But I refer you for the particulars to the paper by Johnson that's now available online in Statistics in Medicine.
How do I get a good estimate of interclass correlation that I can expect in my study?
Getting estimates of interclass correlation can be a bit challenging. It's been a request, I can't say a requirement, for some time that investigators publish interclass correlation estimates from their studies. And if people would do that in their primary outcome papers, that would help everyone else who's trying to plan studies. I've published a series of papers over the last 10 or 15 years reporting interclass correlations for a variety of outcomes in a variety of contexts. You can refer to those. So there are many sources of interclass correlation out in the literature, but you're not going to find it for every variable that you're interested in and every situation that you're interested in. The estimate that you want is an estimate of interclass correlation for the dependent variable that you're going to use, measured the way that you're going to measure it, in the same target population that you have for your study, which means the same age group, the same racial ethnic mix, same rural urban mix, and so forth. And you may not find that estimate. And the further away from that sort of ideal setting that your estimate is, the less reliable it's going to be. Also, if it's based on a very small number of groups, it's not going to be very reliable. You may have to go to pilot data that you've collected, or find a colleague who has data on the population that you're interested in, the outcome that you're interested in, analyze those data. If you can find data that have information on the groups like the ones you're going to work with, the outcome measured the way that you want to measure it, you can analyze those data and get an estimate for the interclass correlation. And there are methods easily available in the literature for how to do that.
You recommend mixed models for the analysis of data from a group randomized trial or an individually randomized group treatment trial. What about randomization tests?
Randomization tests can work very well. Mitch Gale published a paper in 1996 in Statistics in Medicine. I referred to it earlier. He was talking about the use of randomization tests in the COMMIT trial, which was a large study funded by the National Cancer Institute to evaluate a smoking cessation intervention. They randomized whole communities. The study was done some time ago, and so mixed models were not as well developed at that time as they are today. And even today, conservative clinical trial statisticians can get nervous about the number of assumptions that are built into model-based methods, especially mixed models and complicated designs. And so there is a preference among some of those folks, and there was with Dr. Gale, to consider randomization methods to analyze data from a group randomized trial. In a randomization test, which is like a permutation test, first we analyze the data as we did the study and get an estimate of our treatment effect. And then recognizing that the 10 communities that landed in the intervention arm and the 10 that landed in the control arm landed there as just one possible arrangement of communities in arms that could have happened under the null hypothesis, We then systematically look at every possible arrangement of communities and arms, calculate the treatment effect for every one of those, and if I've got 10 and 10, it's a lot, so you need a computer to do it. But now I've generated the distribution of all possible treatment effects given the communities that I used in the study, and I can look to see where the one I observed falls in the distribution. The proportion of the distribution as large or larger than the one that I got is the p-value for my intervention effect. If 3% are as large or larger, my p-value is 0.03. I declare victory and report a treatment effect. The beauty of the randomization test is that there are no distributional or other assumptions required. I simply have to do all the permutations and estimate all those intervention effects. And in that context, it's a huge advantage. It's the reason that many conservative statisticians like it. At the same time, if it's a smaller study and there is confounding in the data, the randomization test is not going to address it. It's not going to get rid of it. It's not going to solve it. And we still need to consider some kind of adjustment of the data to deal with the confounding. The adjustment that's appropriate is some kind of a regression adjustment for confounders in a first stage where I'm calculating group means or group slopes or group rates. And then in the second stage, I analyze those adjusted means or rates or slopes and with a t-test and get my effect, or I do the all possible arrangements and get a p-value. As soon as I introduce those kinds of adjustments, I'm making many of the same assumptions that I would have to make in the model-based approaches, and so randomization tests lose some of their advantage. But they're fine. If properly implemented, I would trust them absolutely. And there are circumstances where I would recommend them over the model-based methods, over mixed model regression methods. For example, if I have a particularly small study, if the interclass correlation is large, if there is, those are the two primary features. Now, I try to avoid those circumstances, but if I'm stuck with it, then the randomization test is going to more closely adhere to the nominal type 1 error rate than the mixed model regression methods.
In studies that extend over a long period of time, it's likely that members will change groups over time. For example, students may move from one intervention school to another intervention school. What do you do if that happens?
Okay, this is also an important consideration. The methods literature in group randomized trials not only assumes that we have the same number of groups and the same number of members in each group, but it assumes that people are only in one group and they don't change groups over time. And having done school-based smoking prevention research for many years, I know that students change schools. They move. They may leave the district altogether. They may move from one junior high school in the district to another. We're not talking about changing conditions. We're not talking about suddenly moving from a treatment school to a control school. This is simply moving from one school in a given arm to another school in the same arm. If they were to move to a school in a different arm, the intention to treat principle would require that I treat them as though they had stayed in the same arm and avoid problems with the crossover. The changing schools, though, coming back to the question that you asked, if members change groups over time and we ignore that, that can further increase the type 1 error rate inflation, so it does create a problem. We have a paper, it's the last one on this page, Rebecca Andridge at Ohio State and Abby Chauvin, Keith Muller. This one is also in statistics in medicine, and we were looking at what happens in group randomized trials and individually randomized group treatment trials when subjects belong to multiple groups. We have another paper that's still under review that Abby Chauvin is leading that looks at what happens when they change groups over time. But the result is essentially the same. You need to pay attention to it. It's important to pay attention to all of the groups that a person is a member of, whether they're simultaneous or sequential, and to model that accurately in the analysis. Otherwise, we can have an inflated type 1 error rate.
I've seen papers that have tested the interclass correlation to see if it was greater than 0 and then ignored it if it was not. Is that okay?
No. I'll elaborate. An intra-class correlation of 0 means that there is no relationship, no greater relationship among members in the same group than among members across groups. In every group randomized trial, especially, and individually randomized group treatment trials where there's a lot of interaction, we can expect some positive intra-class correlation. ICCs are small. It varies depending on the nature of the group and the size of the group. If I've got schools or work sites or certainly whole communities, the inter-class correlations are going to be very small. But if I get to go to classrooms, these are smaller aggregates, the inter-class correlations will be larger. And if I get to very small aggregates like families, they'll be quite large. Spouse pairs, the inter-class correlation could be 0.6 or 0.7. In communities, it might be 0.001. Regardless, if I'm measuring a lot of people in each of those groups, a large M multiplied by a small ICC can still give me a fairly large inflation factor and increase the type 1 error rate if I ignore it. The standard errors for variance components that are close to 0 are not well estimated. Degrees of freedom are often limited. It's a lousy test. So just because you've done a lousy test and shown that there's no significant difference from 0 doesn't mean that it really is 0. So my advice and the advice of all the other experts that have written in this area is to model the inter-class correlation. If it's not very large, it won't hurt you very much, but ignoring it can hurt you.
Group randomized trials seem much more complicated than regular clinical trials. How can I judge if I have to use these more complicated methods?
Group randomized trials are more complicated than randomized clinical trials. It's part of what makes them fun for me and stimulating intellectually, but they're also challenging to do and challenging to design, challenging to analyze. I often say that I used to spend as an academic about half my time trying to talk people out of doing this kind of study, and the other half of my time trying to help people that had to use this approach do it well. So it really comes back to an early slide on the nature of the intervention. When I'm sitting down either as a consultant or as a collaborator, in my initial conversation, I ask people to describe the study that they have in mind, and particularly to describe the intervention that they're going to do. How is the intervention delivered? What does it look like? What's the context? If it's an intervention that can be delivered one at a time to individual people without risk of contamination, that's what you should do, and just avoid group randomized trials and individually randomized group treatment trials altogether. However, the intervention is designed to include group interaction and social support, whether that's virtual on a chat line or live in a classroom or some other context, and that's a critical and essential part of the intervention, then you're stuck and you have to use these methods. If you're doing a school-based program and you think you can deliver it to individual students in the nurse's office, that's fine so long as the students don't go back to their class and start telling all their friends about it, including kids in the control arm. So if you're concerned about contamination or if the nature of the intervention requires interaction, then you need to use these methods. But if your intervention can be delivered without risk of contamination to individuals, then you can use the more traditional randomized clinical trial methods and be just fine.
Can methods that use generalized estimating equations be used to analyze data from a group randomized trial?
They can be. So generalized estimating equations. GEE, this is an approach developed in the 80s by a couple of terrific statisticians at Hopkins. GEE was developed for analyzing longitudinal data. But it has a great feature in that the approach is asymptotically robust, I'll explain that in a minute, to misspecification of the correlation structure of the data. In longitudinal data, that's correlation over time, and you don't have to model that correctly if you're using GEE, and you can still get a valid result. In a group randomized trial, it can be the interclass correlation that you don't have to model correctly and still get a valid result. GEE can be used, but it has to be implemented correctly, and there is a limitation that we have to recognize. It was developed for longitudinal studies where we have hundreds of participants, lots of degrees of freedom. Group randomized trials often have limited degrees of freedom at the group level. If the degrees of freedom are much below 40, traditional GEE methods will have an inflated type 1 error rate and should not be used. There are some small sample corrections that have been developed. Some of those are implemented in some of the common software packages now, like SAS. So if we use one of the small sample corrections, we can be okay. But just straight GE, especially with small group randomized trials, not a good idea.
What kind of people do I need on my team if I'm going to plan a group randomized trial?
That's a very good question. So somebody's got to worry about the intervention. That's often the principal investigator, but not always. Somebody has to worry about the intervention. The theoretical underpinnings of the intervention, putting the pieces together. Somebody on the team has to be familiar with the setting where you're going to do the study. So you're crazy to go to plan a school-based group randomized trial and not have somebody on your staff who's a school teacher and who knows how that system works and knows how to interact with teachers and principals and the other staff in the building. You're crazy to plan a hospital-based group randomized trial and not have somebody on your staff that's worked in a hospital and knows how that operation goes. So you've got to have somebody that understands the context or the environment that you're going to work in. You've got to have experts on the measures that you're going to use. Whether it's understanding how electronic medical records work or understanding how to validate self-reported smoking measures or whatever. You need expertise in the measurement methodology. You certainly need expertise in design and analysis as it relates to group randomized trials or individually randomized group treatment trials. 20 years ago, that was hard to find. Not today. It's easy to find. Mixed models are taught in every statistics and biostatistics program, and if you reach out to colleagues on your campus, you will find somebody who's familiar with those methods, and if they haven't done a group randomized trial before, they can do a little reading and get up to speed pretty quickly. So that is far easier than it used to be. But it would be a mistake to plan and launch a group randomized trial without having expertise in the setting, the intervention methods, the measurement methods, certainly the design and analytic methods, and there may be other issues that you need as well.
Well, thank you, Dr. Murray, for all of the useful information. Also, thank you for everyone who has participated in today's webinar. Stay tuned for future Mind the Gap seminars by checking our website regularly at www.prevention.nih.gov.
Thank you.